Okay, so if I'm looking at my spring here, and here's its equilibrium point, my amplitude could be where it stretches here and my spring is stretched all the way out to my maximum, or it could be when my spring is really compressed and it's sitting here. Okay, so my amplitude can be both positive in this direction or negative if it's compressed in that direction. Okay, does that make sense? I know it's quite the drawing. Okay, but our amplitude can go either way, so we can have a positive amplitude when we stretch it or a negative amplitude when we compress. Frequency is kind of the, what's it called, reciprocal of period. That's the number of oscillations per second. Okay, and now we kind of give frequency a new unit, which is hertz, Hz. Okay, which is essentially one oscillation per, oscillations per second. Okay, or all right, wavelength is given by this Greek letter. Okay, so when we're talking about wavelength, we want to think about one complete cycle. So if I have a wave here, my wavelength might be from peak to peak. Here's a wavelength, or trough to trough. There's a wavelength, or it could be anywhere in between, but it has to be identical portions on the wave, okay, or identical places on that wave. Okay, so there would be our wavelength. Okay, and it's also measured in meters. You probably won't have to write that one down, but velocities measure distance per unit of time. So we still measure wavelength and the speed of wavelength in meters per second. Okay, how far is that wave traveling, or how fast is that wave traveling? Yeah?
So oscillation will always know that it's complete only when it gets back to its starting place?
So in a wave, like I just showed a wavelength and an oscillation are the same for a wave, right? It's one complete set. Okay? All right, so here's another example of our wave. If we're looking specifically at waves, wavelength might be from peak to peak, like I showed. Amplitude is always from your equilibrium point to the top. Your amplitude could go to the bottom as well. Okay, so my amplitude could be this distance as well. Okay, and I'd have negative amplitude there.
And do we take the absolute value or make it negative?
You would make it negative. Okay, questions so far? All right. We're going to look at the connection here between frequency and period. We remember that equation right there, F equals 1 over T. We've seen that before. Okay? So now we're going to kind of connect that basically with velocity, the wavelength, and the period or frequency of our waves. Okay? So this equation on top is not new, but these two are new. Okay? So now we can take velocity equals wavelength over time, right? How long the wave is divided by how long it takes to travel. Or we can take velocity equals wavelength times frequency, because those are essentially just reciprocals of each other. Okay? So those are two new equations that you want to have down, probably on your equation sheet. Okay, so if you want a new equation sheet for this chapter, you can come grab one. But you will probably want that equation or those two on your equation sheet. So we've talked kind of about what the waves look like, what the simple harmonic motion looks like. Now we're going to talk about how we connect energy to that. Okay? Potential energy of a spring. Does anyone remember that equation off the top of your head? Potential energy of a spring? 1/2 kx squared. Good. Potential energy of a spring is 1/2 kx squared. And what's our k value? The spring constant. And is it a number that we know all the time, or is it individual? It's individual. Very good. Okay. Each spring has its own spring constant. Okay. So potential energy of a spring is given by that equation. We know the total mechanical energy of any system is potential plus kinetic, right? So if we're looking at a spring in this case, the energy of that particular spring 1 half mv squared is the kinetic, 1 half kx squared is potential. So if it's in motion, if our spring is moving, it's going to have both of these things, right? Both potential and kinetic. Okay? If it's stretched all the way to its max, what would it have? Only potential. Okay? And if it's compressed all the way to its max, what would it have? If it's compressed all the way to its max, it would also be potential. Okay? Because it has the potential to uncoil and go. If it's at its equilibrium point, what would it have?
Equal kinetic and
All kinetic. It would have all kinetic because it has no more potential. If it's at its equilibrium point, it's done its job. Okay? But then as we start stretching it, then it gains potential again because it wants to bounce back to its equilibrium. Okay? When we're looking at springs and we're talking about these systems, we can assume that everything is going to be conserved here because we're working in a perfect physics world, right? No friction, no air resistance that's slowing down that spring. We're talking perfect physics world here. Okay? Okay, so let's take a look at this spring, okay? And we kind of talked just about what this would mean, but we're going to look at each of these examples. Okay, if the mass is stretched or compressed to its maximum, all energy is potential. So that means here, is the spring stretched or compressed? It's compressed. And here we have an equation, 1 half Ka squared. What's the A mean? What's A stand for? Amplitude, good. Okay, and we just learned in our vocab that that's the maximum displacement. Okay? If the mass is at its equilibrium point, we just discussed it has all kinetic energy there because it's got no more potential. The spring is exactly how it wants to be. When we stretch it, it's got only potential there. Okay, it's at its turning point. Oh, sorry, right here. It's at its absolute max in the positive direction now, so it's at its turning point. It wants to start going back to its equilibrium. If it's somewhere in between, either way, it's going to have both. Okay? I know we just kind of talked about that, but I want you to see it in the actual visual right there. Talking about things beside a spring, period of a simple harmonic oscillator. We're talking about things beside a spring. We don't even care about the amplitude. We don't care about the distance it's traveling. The only thing that matters is the stiffness of the spring. Okay? So when we're talking about something, I said except springs, but when we're talking about these simple harmonic motion and how quickly these things move, okay, and their identical repetitive motion, we really don't even care how far it's traveling. Okay? We can find the energy by using the amplitude, but the period and the frequency of this spring moving in simple harmonic motion makes no difference about how far it's traveling. Okay, it matters the mass of the whatever's on the end of the spring, and it matters how stiff the spring is, or the spring constant. Okay, so these are two equations that we can use for a simple harmonic oscillator, something that's moving in this simple harmonic motion.
So was that last little note saying that period would be in seconds?
Yes, period should be in seconds. Mm-hmm.
On the E equals 1 half K with the amplitude in the equation, is amplitude squared?
Amplitude is squared, yes, I'm sorry. Okay, so let's go ahead and start writing this problem down. Get whatever written down you need to, and we'll start working out together. Okay, so what's this first value tell us? 80 Newton divided by meters. What is it? It's our spring constant, right? So this is our K value. And this tells us the mass. So M equals 0.60 kilograms. Okay, we want to find the period of the motion. So are we solving for T or F? T. We need to use that equation for T. Okay, and that equation looks like this. T equals 2 pi square root of M over K. So it's just kind of a plug and chug situation. Okay, plug those numbers in. All right, Michael, what'd you get?
I got 0.544.
That's what I had. 0.544 seconds. Do we agree? Okay, so tell me what this time means to us. What picture of our motion are we looking at here? Is that only the spring dropping down? Is it only the spring going up? What is the motion of this time period look like? Perfect. Down and up, then back to the center. Very good. Okay, period means that whole entire oscillation. Very good. Did everyone get that to come out? Okay. All right, if we want to find the K value of our spring, we can use this equation, which we've seen before. So if we have to solve for that, we can use the K value. If our spring is hanging vertically, like it was in the last case, the force that we would be looking at here is the force due to gravity, right? That mass is being pulled down by gravity that's on the end of the spring. It would be our gravitational force. So we can use kind of a variation, sorry, I'll look at it on the next slide. We'll use kind of a variation of this equation to solve for the spring constant if we need to, if this spring is hanging vertically. And I'll show you an example of that on the next slide here. Okay, so here's our spring that's hanging vertically. When we pull the spring down or when we add the mass, what's happening to the spring on the right? Stretched or compressed? Stretched. Okay, we need to make sure we're good with those terms. Okay, we stretch that spring. So here we would use the force due to gravity is equal to our spring constant times x. What's our x value here? What's this called? Could be amplitude, but displacement, because we're not sure if this is the absolute maximum it can be stretched or not. Okay, but x is displacement. Okay, so to solve for the spring constant, we just rearranged, and all we did here was plug in force due to gravity, or mg. Okay, you don't have to write down this set of equations. That's just kind of how we go about solving for k in that case. And this one takes just a little extra thinking, okay? So before you really get too far into the problem, make sure we're on the same page. Okay, so our goal here is to solve for K, to solve for our spring constant. So let's think about a car and the springs that go into the car's suspension, okay? When we build the car and when we put the springs into the car, do we build the springs so that it's going to compress with the car's weight, or do we build the springs so that they're at equilibrium with only the car's weight? At equilibrium with the car's weight. So what's going to make this spring compress? Is it the weight of the car or the weight of the family? The weight of the family. So we don't care about the weight of the car here. Okay? In this situation, we don't care about the weight of the car because it's at rest and only the family is adding weight. If the car is in motion, if the car is bouncing, yes, then we're going to take into consideration the weight of the car and the family. But this car is at rest, they're just getting in it. Okay? So let's think here. If we want to solve for K, we're going to take the force due to gravity of the family. Okay? So we'll rearrange K equals F over X. 200 times 9.8 over 3 centimeters, which means it's 0.03 meters. Okay, Andrew, what'd you have? 65,000 what? Good. Do we all agree there? Good. Okay, does it make sense why we're not taking the value of the car?
Good morning. In just a moment, I'm beginning calling.
Of just these two sides. Okay, how far will the springs compress if the mass was 300 instead of 200 kilograms? Okay, that's just an easy change in the equation. So if the family weighs 300 instead of 200, that changes, okay, that changes our compression. Does the spring constant change? No. Okay, so we keep that same spring constant value. All right, Jackie, what'd you have for X, for your displacement? Oh, sorry. Good. 0.045 meters. So if we wanted to put that into a more relatable value, what would it be? More relatable to our first.
4.
Yeah, 4.5 centimeters. Okay, so that tells us that we have a pretty decent increase in our displacement. This one tells us a fly with a mass of 0.15 grams, careful there, grams, is caught in a web that vibrates at 4 hertz. What's the spring constant of the web?
At this time, the top floor may go to the gym.
If you haven't yet, go ahead and get it written down, and then we'll go ahead and go through it. All right, so this is using our new frequency equation. Frequency equals 1 over 2 pi square root of k over m. Okay. We're given our frequency of 4. And we're solving for k. So we're going to have to unpack this mathematically a little bit. Did everyone remember to convert their grams to kilograms? 0.00015. All right, so mathematically, I'll kind of show you how I do this. I might not be the correct exact way, but I'm going to go ahead and move 2 pi over to the other side first. Okay, and how do I move that 2 pi over? Multiply it over. So I'll take 4 times 2 pi, which I'll just leave it as 8 pi right now, equals square root of k over 0.00015. Next, we should, good, square both sides. Okay, and that leaves us with 8 pi squared equals k over oh, I'm sorry, you can't really see that. 0.00015. Then I'm just going to multiply across. All right, so solving for k, what'd you get, Gabe?
0.0947.
Good. Good, 0.095 or 0.0947, very good. All right, feeling okay about that so far?